So the second application that we're going to talk about is doubling period or exponential growth. So bacteria, they reproduce at an exponential rate. This is called exponential growth. We saw the graph last time. It's an exponential growth because the base will be a whole number, in this case 2, and that means that we have an always increasing exponential function. We have a specific term for exponential growth called the doubling period or the doubling time. So the doubling time for a specific species of bacteria is the amount of time that it takes for that is required for the population of the bacteria to double. So let's think back to half-life. Half-life was the amount of time that it takes for a radioactive element to have its mass. So to go from 10 grams to 5 grams, how much time does that take? That's half-life. To go from 2 grams to 1 grams, 1 gram, how much time does that take? That's half-life, because it's the amount of time that it takes to half the mass. With doubling time, we're looking at the amount of time that it takes to double the population. So if there was initially 50 bacteria in a colony and they doubled to 100, how much time did that actually take? Or if there was only 2 bacteria in a colony and then it doubled to 4, how much time did that take? So just like yesterday, we're going to start off by answering this question using logic, and then we'll go back and see how we can use the equation. So E. coli, also known as Escherichia coli, has a doubling period of 20 minutes. What does that mean? Every 20 minutes, we have double the number of E. coli, or that bacteria. And this is just a fun fact, why bacteria spread so quickly, because most of them do have very small doubling periods. In this case, within 20 minutes, you can have double the number. So if you start off with just 100 bacteria on a surface, let's say your desk, within 20 minutes, you have 200. The next 20 minutes, you have 400, so on and so forth. What would the population of E. coli be after 6 minutes? If the initial population had 150 bacterial cells. So let's start with what we did yesterday. So we'll start with our initial amount. Our initial amount at t is equal to 0 is 150 bacteria cells. So initially at t is equal to 0, we had 150 bacteria within our colony. We know that our doubling period is 20 minutes. So t is equal to 20 minutes. Again, I'm going to go back and put minutes here. 20 minutes, we expect this colony to double. So we had 150 initially. 20 minutes later, we expect it to double to give us 300. So again, that's what the doubling period means. Every 20 minutes, we expect the number of bacteria to double. So Escherichia coli has a doubling period of 20 minutes. What would the population of E. coli be like after 60 minutes? So after 20 minutes, it went from 150 to 300. Let's see what happens after another 20 minutes. So again, that's another doubling period has passed. So 300 will double and become 600. But we don't want to know how much there will be at 40 minutes. We want to know how much there will be at 60 minutes. So that's just another doubling period. And that will be double what there was at 40 minutes, which is 1,200 bacterial cells. So what did we see? We said we started with 150 bacterial cells at 0 minutes. Every 20 minutes, the population doubled. So 20 minutes later, it went to 300. Then 20 minutes later, it went to 600. Then 20 minutes later, it doubled again and went to 1,200 cells. So in an hour, within an hour, a colony of 150 bacteria can become 1,200 or 1,200 bacterial cells. This is specific for E. coli. So E. coli has a doubling period of 20 minutes. Other bacteria have a different amount of time which they take to double. So we can also solve this question using a formula just like we saw yesterday, or in the previous video. So here is our formula. So I, again, represents the initial number of bacterial cells. So how much did you start with? Again, here it would be 150. A represents how many bacterial cells exist after a specific amount of time. So here, for this scenario, A would be 300 because after 20 minutes, we have 300 bacteria. Here, A would be 1,200 because after 60 minutes, we have 1,200 bacterial cells. Just like yesterday, the A and the I must have the same unit. So these two must have the same units. And then T is the actual time that passed. That's the same as yesterday. And D is the doubling period of the bacteria. So instead of having H here for half-life, we have D here for doubling period. And just like yesterday, both of these must have the same units. So that's the formula. Yesterday, we applied this formula to every single scenario to make sure it worked. Today, I'm just going to apply it to a few scenarios just to make sure it works. So let's do this one and this one. So we have A is equal to I. Initially, we had 150. A time is equal to 0. So 150 times 2. So half-life, the base was half. For doubling time, where you go twice as big, the base is 2. The time that passed is 20 minutes divided by the D, the doubling period, which is also 20 minutes. So here we have 150, 2, 20 over 20 is just 1. So 150 times 2, which is 300 cells. Again, initially we measured bacteria in cells, so our final amount is also in cells, the same units. Let's do this one as well, because we can. Here we have 150 as the initial, 2 as the base. The time here is 40 divided by the doubling period, which is 20. So we have 150, 2 to the power of 40 over 20, which is 2, which is 150 times 4, which is equal to 600 cells, which is exactly what we got here. Same thing here. We have A is equal to 150, 2 to the power of T, which is 60, over 20, which is the doubling period. So that's 150, 2 to the power of 3, which is 150 times 8, which is equal to 1,200 cells as well. Okay, so we know that the formula works. Again, we have the time divided by the doubling time, which left us with 1 here, 2 here, and 3 here. Remember, these just represent the number of growth periods, or the doubling periods. So here, the doubling time is 20 minutes. 20 minutes passed, so we had 1 growth period or 1 doubling period. Here, the doubling time is 20 minutes, but 40 minutes passed, which is 2 of the doubling periods. So here we had 2 growth periods. And here we had 3 growth periods because each growth period is 20 minutes and 60 minutes has passed. So when you divide it, the exponent you're left with when you simplify your exponent, that just represents the number of growth periods. So now that we have this knowledge, let's go and apply our knowledge. So here, a population of bacteria contains 1,000 cells. The doubling period of the bacteria is 4 minutes. How many bacteria will be in the population after 12 minutes? So the population of bacteria originally had 1,000 cells. Let's write that in. 1,000 cells. The doubling period is 4 minutes, so we can write that in. And how many will exist after 12 minutes? Well, that's the time that has passed. So we want to figure out the A, how many will exist, how many bacteria cells will exist after 12 minutes. Again, write in the formula. So again, the A and the I are in the same position. The half from the half-life becomes a 2 for doubling time. And instead of T over H, we have T over D. But other than that, the formulas are quite similar. Once you have the formula, write down the physical amounts. So replace the variables with the known amounts. We don't know A yet, so keep that. I is 1,000. Keep the 2, and T over D is 12 over 4. So we're left with A is equal to 1,000. Remember, you always want to simplify the exponent first. 12 divided by 4 is 3. So the amount is 1,000 times 2 to the power of 3 is 8. So amount is 8,000. One thing I forgot to do, which you should always remember, is make sure these units are the same first, and make sure these units are the same as well. So the I here is cells, so the A should be measured in cells as well. So A is 8,000 cells. Again, this is a word problem, so write down a final sentence. There will be 8,000 cells in the colony after 12 minutes. Okay, so once again, what does this 3 represent here? 3 growth periods. Each growth period was 4 minutes. If we pass 12 minutes, that means we've passed 3 of those 4-minute periods, or we've passed through 3 growth periods. At each growth period, the bacteria will double from its previous amount. Let's look at this example. The doubling period of Staphylococcus species, is 30 minutes. After 90 minutes, there are 72 bacteria. What was the initial population of the bacteria? So again, the doubling period is 30 minutes. We can write that down. After 90 minutes, so that's T, that's the amount of time that has passed, there are 72 bacteria. So after the time that has passed, there's 72 bacteria left. What was the initial population? So we're solving for the I this time. So again, write down the formula and start filling in the numbers you know. So the A in this case is 72. The I is unknown, so we're going to leave it as is. The base is 2. The time is 90 divided by the D, which is 30. So 90 divided by 30. So here we have 72 is equal to I. Remember, you always want to simplify the exponent first. 90 divided by 30 is 2. Oh my gosh, and I forgot it again. Make sure the units are the same before proceeding. Okay? So here we have, so you simplify the exponent. So you have 72 is equal to I. 2 to the power of 3 is 8. And now to isolate for the I, I'm going to divide both sides by 8. So this side I'll divide by 8, and this side I'll divide by 8. These will cancel out. 72 divided by 8 is 9. Again, you're using the same units as the A, so this is 9 bacteria or 9 bacterial cells. Again, this is a word problem. Don't forget to write down the final solution in a sentence. So the initial population of bacteria is 9. So 9 cells, for example. Good. We'll do one more example. So just give me 2 seconds as I switch to the next sheet. So the last question we have here, again, let's read through it, write down all our information. The doubling period of a Streptococcus species is 42 minutes. So let's write that in. 42 minutes is the doubling period. If there are initially 26,000 bacteria, so that's our initial amount, 26,000 cells or bacteria, how many bacteria will there be after T 65 minutes? So again, we're solving for A in this case. So let's write down this equation. So A is equal to I to T over D. Once you write it down, start filling in the information that you've been given. So here, the initial amount, we're solving for A, so we're going to leave that blank. The initial amount is 26,000, but before I put it in, I'm going to make sure the units are the same. So these are both minutes, so they're good. Both of these have to be the same units, so we know we'll measure them in cells. So the initial amount is 26,000. We'll copy the base. The T here is 65, and the D here is 42. So what you'll notice here is that these aren't nice numbers. All of the questions we've been working with so far, the exponent reduced to a really nice number, then we were able to solve. In some cases, we might need to go to our calculator, like in this case. So we'll still follow the same rules. So we have A is equal to 26,000. 2, we'll simplify the exponent first. So here we have 65 divided by 42, which is 2 to the power of 1.547619048. And now I'm going to put this into my calculator. You should have specific buttons to help you do this. So I'm going to put in 26,000, bracket to bracket to represent the base. And to put in an exponent with a random number like this, you're going to press this button that has x to the power of y. And then because this number is currently stored in my calculator as the answer, I'm going to press in answer. And that should give me about 76,006.9 bacteria. So I'm going to write out the full answer first. So 76,006.91458. Again, these are bacteria cells. We can't have a fraction of a cell, so we know we need to round, and we'll round up to 76,007 bacteria cells. Again, because it's not an exact value, we use the squiggly lines to indicate this. So this is around 76,007 cells. So I'm just going to make sure something. Okay, and that is correct. So now we have our answer. So we have to write our sentence. So there will be 76,007 cells after 65 minutes. So I want to show you this just to show you how you can do this with your calculator, but in reality, most, if not all of the questions I'll give you will use nice numbers, so you should be able to solve them on your own. So I'm going to reduce your homework a bit. Okay, so handout G, you've already done 4 and 5 for half-life. Now you're going to do number 1 to 3 for the growth. So exponential growth, the doubling periods. I want you to try these as well. So try these, send them in, but I want you to definitely do handout G and send it in. Thank you.